Resistance. In this lesson, we're talking about loads, insulators, conductors, superconductors, Ohm's law, power, and calculating total resistance. Key term, resistance. When the electrons pass into a device, a load, they bump into other substances within the object, so ions, other electrons, etc. These bumps interfere with the electron flow because they get in the way. Think of it as kind of like a Plinko machine too, if you've ever seen something like that, where you have different objects laid out inside the Plinko machine, and if you drop a ball, it's going to come down here, hit that, deflect that way, and it's going to keep deflecting until it reaches the bottom. And the more of those deflections there are, the more resistance it's facing. Electrical resistance is a property of a substance that hinders electric current and converts electrical energy into other forms, such as heat. The more bounces here, 1, 2, 3, the more heat that would be generated. And this is again similar to how a ball is going to move down our Plinko machine or through a pinball machine. Loads. A resistor or any other device that transforms electrical energy into heat, motion, sound, or light is called a load. So examples include things like watches, flashlights, lights, computers, etc. Resistance. Some substances resist the flow of electrons better than others. These are called resistors or insulators. Light bulb filaments are very good resistors, and you can see the filament located right there. It's this metal part, it's glowing, but usually it would be a dark color and it looks something like that. They slow down the electrons that pass through them, which allows them to remove more energy from the electrons, making them glow. So they're going to remove the energy from the electrons, they're going to heat up, and they're going to glow as a result. Some substances don't resist the flow of electrons well. These substances are called conductors. Conductors are substances that carry electrical energy without much resistance, little loss of electricity. Copper and aluminum are very poor resistors and therefore make good conductors. So I want you to explain why being a poor resistor would make copper and aluminum good materials for electrical wiring. So pause the video, think about it, write your answer down, and then we're going to come back to it. Okay, got your answer? Well, the main idea is that if we want to go from point A to point B and we want to move electricity from those 2 points, we don't want to lose much electricity. Unlike the filament in the previous slide, where we want to lose the electricity so they would generate heat and light, when we're just moving electrons from one place to another, we don't want their energy to be lost so that we have more available at B. So for instance, if we left A at 100 joules, we want to arrive at B with as close to 100 as possible. 100 would be ideal. However, we are probably going to lose a little bit in the journey. But the less we lose, the more that's available at B. Now, copper and aluminum do this very well. They're very good conductors, they're poor resistors, so most of the energy that starts at point A makes it to point B. So what determines the resistance of a wire? Well, the type of material. Different materials have different degrees of resistance based on their molecular composition. So copper will have a different resistance than aluminum will, which will have a different resistance than, say, gold or silver. The length. The longer the wire is, the greater the resistance. So wire A will have less resistance than wire B. The diameter. A wire with a large diameter has a lower resistance. So big diameter, lower resistance than a thin wire. Think about if the electrons are moving from point A to point B, we want them to bump into things the least amount of times as possible. If you have a wider diameter, there's less chance of it hitting the walls. Think about if you're walking down a hallway. A wider hallway will allow more people to pass by without bumping into each other than a really crowded, narrow highway. And then the temperature. A hotter wire has a greater resistance than a colder wire. Superconductors. When electric charge can flow through a material with no resistance, the material is called a superconductor. Obtained by cooling to almost absolute zero, these superconductors vastly increase the efficiency of the wire because all the energy is carried forward, so none is lost. So we talked about copper being a good conductor. Well, a superconductor would have 100% of the energy transferred from point A to point B with zero lost. And it's used in materials that carry a lot of current, so a lot of electrons. The more current there is, the more electrons that are passing through the wire, and the greater the chance of energy being lost as it's transferring from point A to point B. So what are some applications of superconductors? Well, due to their zero resistance, superconductors have many practical applications, including maglev trains, like we have here in the top picture. So the train actually sits on a magnetic field, so it's not touching the rails themselves. This reduces friction and allows greater propulsion and less wear and tear on the vehicle. Faster computers, MRIs, particle accelerators, electric generators, sensors, and zero-loss power cables are other examples of practical applications of superconductors. Ohm's law. Free electrons tend to move through conductors with some degree of friction or opposition to motion. We talked about superconductors having zero resistance. Well, most substances aren't superconductors, and therefore there is some resistance as electricity passes from one substance to another. This opposition to motion is more properly called resistance, like we've talked about. And the symbol for resistance is the ohm. Now, the simulation in the bottom right-hand corner of the screen here is very good. So pause the video and have a look. Ohm's law. As resistance increases, current decreases. So as we increase resistance, we decrease current. The higher the resistance, the more the electrons will slow down as they pass through. As the electrons slow down, their energy can be taken to do work. For instance, light up, move a motor, etc. The Ohm's law formula is V equals I times R. So current equals voltage times resistance. So again, I want you to pause the video and I want you to try this simulation here. Check your understanding. What is the voltage drop across a 100-watt light bulb if the resistance is 150 ohms and the current is 0.8 amps? So voltage is the question, resistance is 150 ohms, and current is 0.8 amps. Our formula equals V equals I times R. 0.8 times 150 equals to 120 volts. Power. What gives lights their brightness is the power. The formula for power equals P equals V times I, where V is voltage and I is current. The units for power are watts. 1,000 watts equals 1 kilowatt, and that's going to be important to keep in mind. Remember that V equals I times R, and if we increase the resistance, we decrease the current as V stays the same. So if you think about the voltage that comes out of your walls at home, that voltage is going to stay constant at 120 volts or 240 volts, depending on where you live. So the voltage is going to stay constant. So when we do our calculations, that's going to be something that we're going to be able to keep in mind. If current decreases, power decreases. And why is that? Well, using this formula right here, so P equals V times I, if we're going to keep voltage the same, and we're going to decrease current, if we decrease the right side of the equation, we're going to have to decrease the left side of the equation as well. This means less power, so your load can't do its job quite as well. An example of that could be your light wouldn't be as bright, so if we decrease the current, the light would dim. Check your understanding. Bulb A has a resistance of 2 ohms, while bulb B has a resistance of 4 ohms. Which bulb, A or B, has a greater electrical power? And the voltage across each bulb is 5 volts. So V equals 5 volts, and we'll just say that's A, and we'll call that B, so voltage is 5 volts. Bulb A has resistance of 2 ohms, and bulb B has resistance of 4 ohms, and we're looking for power. Power is going to equal to V times I. For bulb A, power is going to equal to 5 times I, and we don't know what I is. And for bulb B, power is going to equal to 5 times I. So how are we going to figure out I? Well, for bulb A, we're going to use our first equation here. V equals I times R. And we're going to rearrange to solve for I. So we're going to say that I is going to equal to V divided by R. Voltage we were just told is 5 volts. And the resistance for A is 2 ohms. 5 divided by 2 is 2.5 amps. So we can plug that in. We'll also solve for B. V equals I times R, same as before. I is equal to V divided by R, 5, and the resistance for B is 4. You take 5 divided by 4, you get 1.25 amps. So now we can plug those numbers in. So for bulb A, we're going to say power is going to equal to 5 times 2.5, which equals 12.5 watts. For bulb B, we're going to say that P equals 5 times 1.25. So power is going to equal to 6.25 watts. Calculating resistance in a circuit. Total resistance, or RT, is calculated differently depending on the type of circuit. If you're talking about a series circuit, all you're going to do is you're going to add up, so it's going to be R1 plus R2 plus everything in between to give you your RT. So if R1 was equal to 4 and R2 was equal to 3, then you would say that RT is equal to 4 plus 3, which is equal to 7. So that's pretty basic, and that would be ohms. But in parallel, it's more complicated. It's 1 over RT equals 1 over R1 plus 1 over R2 plus so on and so on, all the way to 1 over Rn. So it's a little bit more complicated. So if we use the same example where R1 was 4 and R2 was 3, we would say that 1 over RT equals to 1 over 4 plus 1 over 3. If you put 1 divided by 4 plus 1 divided by 3 into your calculator, you'll find 1 over RT is equal to 0.583. But that's not the complete answer, because we need to find actual RT. So to find RT, we're going to take the inverse of our answer. So we're going to say RT is equal to 1 over 0.583, which is equal to 1.7 ohms. Check your understanding. Find RT and IT using the circuit below. So the first thing we need to do is we need to take a look and see what kind of circuit it is. It is a parallel circuit. So since the parallel circuit, and we know that the voltage is 12 volts across the battery, we know that V1 will equal to 12 volts. We know that V2 will equal to 12 volts. We know that V3 will equal to 12 volts. And we know that V4 will equal to 12 volts. Now we can figure out most of the rest of the stuff just by taking our formula V equals IR. So to find I1, we're going to take V1 divided by R1, which is going to equal to 12 divided by 10, which is equal to 1.2 amps. I2 is going to equal to V2 divided by R2. V2 is 12, R2 is 20. 12 divided by 20 is equal to 0.6 amps. I3 is going to equal to V3 divided by R3, which is going to equal to 12 divided by 10, which is 1.2 amps. And I4 is going to equal to V4 divided by R4, which is going to equal to 12 divided by 1, which is going to equal to 12 amps. So now we need to find IT. Well, we know IT, since the parallel circuit, we're going to take the current from here, add it to there, that one, and that one, and that one. They're all going to add together. So IT is going to equal to 1.2 plus 0.6 plus 1.2 plus 12. And that's going to equal to 15 amps. So that's the first answer. The second thing we need to find is RT, and that's going to be a little more complicated. We're going to say that 1 over RT is going to equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4, which is going to equal to 1 over 10 plus 1 over 20 plus 1 over 10 plus 1 over 1. 1 over RT is going to equal to 1.25. Now to find RT, we need to do 1 divided by 1.25, which is equal to 0.8 ohms. And that's our answer. Check your understanding. Find RT and IT using the circuit below. Now the first thing we got to do is we got to figure out whether it's a series or parallel circuit. It's a little bit more complicated because it's actually both. You can see that it's parallel because we have 1, 2, 3 branches, but it's also series because we have this series part here where it goes down the third branch. So first of all, let's solve for the IT, and then we can deal with the fact that it's both series and parallel. So let's solve for I for each of the branches. I1 is going to equal to V1 divided by R1 based on our formula. V1 we know is going to be 12 because that 12 volts is going to be for here, here, and down here, divided by R1, which is 4. 12 divided by 4 is 3 amps. I2 is going to equal to V2 divided by R2. V2 is going to be 12. R2 is 4. And again, we get 3 amps. I3 using the same thing is going to be V3. So 6 divided by 3, which is 2 amps. And I4 is going to be V4. So 6 divided by 5, which equals to 1.2 amps. And now we can figure out I total, because I total is going to be the I from this branch here, plus that, plus that. So it's going to be I1, which is 3, plus I2, which is 3, plus I3, which is 2, plus I4, which is 1.2. And when you add all those up, you get 9.2 amps. So that's the first bit of the question. Now the second bit of the question is a little bit more complicated. To figure out RT, we need to have all the different branches. Remember, it's going to be 1 over RT is going to equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4. But it's not quite that simple because this third branch has 2 loads on it. So we need to combine those two. And we're going to do them in a series circuit. Remember, RT, we'll say RT3. So on third branch, it's simply equal to R3 plus R4. So the total resistance on the third branch is going to be 3 ohms plus 5 ohms, which is equal to 8 ohms. So now we know that R1 for this branch is 4, R2 is 4, and R3 is 8. So now we can solve for RT. 1 over RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3, which is equal to 1 over 4 plus 1 over 4 plus 1 over 8, which equals to 0.625. To find RT, we're going to say 1 divided by 0.625, which equals to 1.6 ohms. That's our final answer, and that's our final answer. And that concludes our lesson on resistance.